Hello friends, so we finally arrive at the end of this course. It has been a long journey and a difficult one, but I really enjoyed interacting with you people, and the response has been good. So I wish you all the best. I hope that I have been able to deliver you some important content in probability theory, and I hope that this will serve as a useful course for your future endeavors. So let me just, I think I have uploaded this course, I uploaded this lecture, but let me not take any chance and just go through it quickly. So we all have till now different modes of convergence. So you have almost sheer convergence, which is the strongest form of convergence. Almost sheer convergence, you have seen, implies convergence in probability. And you have also seen that convergence in probability implies weak convergence or convergence in law. But the converse is not true. That means weak convergence or convergence in law, which is also called convergence in distribution in some texts, does not imply convergence in probability. However, there are some exceptions. The exception being that if xn converges in probability to 0, then it is equivalent to converging in law to x. Or you can, instead of 0, this same result will hold if instead of 0 you have xn converging in probability to some constant. So we are just stating it and proving it for xn converging in probability to 0 in order to make it simple. So so convergence in probability implies convergence in law. So the one part of the proof is very simple. It is the other part that requires a bit of effort. And really what you have to prove that xn converging in law to x, where x is a random variable that takes only one value 0 with probability 1, then it is converging in probability to 0. So what is meant by converging in probability to 0? It means that probability mod xn greater than epsilon goes to 0 for every epsilon positive. Now probability mod xn greater than epsilon is 1 minus fn epsilon and minus fn minus epsilon. Why? Because this will be equal to 1 minus probability xn less than equal to epsilon, right? So a probability of a is equal to 1 minus probability of a complement. So here a complement is xn less than or equal to epsilon. And for any random variable x, what is probability that mod x is mod x less than equal to a? Well, that is same as x is between a and minus a, and that is f of a minus f of a minus for any continuous random variable. So so I am writing this here, and now xn is converging in law to x. So what does that mean? By the definition of weak convergence, that means fn epsilon will converge to f epsilon, where and fn minus epsilon will converge to f minus epsilon, provided epsilon and minus epsilon are continuity points of f, where f is the distribution function of f. So let's find out the distribution function of f, because we know that the exact probability distribution of x. So if we look at the distribution function, that is probability x less than equal to y, obviously it will be 0 for any negative y, because y takes only value that is 0, so it does not take any negative values. And so the probability that y will be, x will be less than any negative number, that is 0. And for 0 it is 1. Why? Because then x is less than equal to 0 means in this case probability x equal to 0, that is the only value, that is 1. And in the same vein, probability x less than equal to y, where y is anything positive, that would that means x taking only one value, that is 0, so that is also 1. So you see, what is this function f look like? It is 0 to the left of 0. At 0 it jumps up at 1 and then remains there forever. So this is a continuous function. It is a function that is continuous everywhere except 0, and the discontinuity point is 0 only. So for any positive number epsilon, f epsilon and epsilon and minus epsilon are continuity points of f. So therefore, by the definition of weak convergence, fn epsilon will go to f epsilon, which is 1, and fn epsilon will go to f minus epsilon, that is 0, from this definition. Therefore you see that this probability will converge to 1 minus 1, and so that is 0. Therefore we have this convergence in probability. So remember, convergence in probability implies convergence in law always, but the converse is not always true, but the converse holds good. That is, convergence in probability and weak convergence are one and the same if and only if the limiting distribution is degenerate. This is, or that is like a constant. That is, the random variable takes only one value with probability 1. In that case, they are one and the same concept. Now, suppose I have got convergence xn converges in law to some random variable x and yn is converging in probability to constant c. So this convergence, whether you say convergence in probability or in law, that is one and the same, because I am talking about converging to a constant. So then what happens to xn plus yn, xn into yn, or xn minus yn? So that is called the Slutskys theorem, Slutskys theorem. Now what the Slutskys theorem tells us is that the xn plus yn or xn into yn will converge to x plus c or c into x, and xn by yn will also converge to x by c provided c is non-zero. So here the important theorem is one of the random variable is converging weakly in law, the other is converging in probability to a constant. So you cannot compromise this thing that a convergence in probability is to a constant. If you find out, if you have a case where xn is converging in law to another random variable, then Slutskys theorem may not hold. Okay, so that's it. And here is an example showing the application of the Slutskys theorem. Here I have got x1, x2, xn, iid, random variable, mean 0 and variance finite. So my query is what happens to 1 by n to the power 0.6 x1 plus x2 plus xn. So 1 by root n into summation of xi, that part you know by CLT goes to n01. Why? Because mean 0 and variance is finite. That is the most important part. And 1 by n you can look as 1 by n to the power 0.1, that you can, or 1 by n to the power 1 by 10, that you can look as yn, that converges almost surely to 0 and hence in probability. So by Slutskys theorem what will happen? This will be the application of this part xn into yn. So this will converge in probability to so what is the c here? C is 0. So yn is converging to 0. So 0 into a standard normal random variable. So it converges in probability to 0. So why I am saying converging in probability? Because it converges in law to 0. That means it is one and the same by the previous lemma. So it goes to 0. So Slutskys theorem is a very important result, like many other results that you have seen, like the DCT, like the Borel-Cantelli lemma, Slutskys theorem, central limit theorem. These are some of the fundamental results of probability theory based on which an entire subject is developed. So no matter what level of probability you do, these will be your kind of lifelong tools. So once again, thank you, and I hope you have learned something from this course. All the best.